environmental application. And also Dr. Choi also mentioned the biochar to make electrolyte. And the solid recovery fuel as the pathway for solid digestate valorization. So Dr. Ting, the floor is yours.
Thank you. Good afternoon. My name is Yu-Chieh Ting. You can call me Danny. So actually, I'm doing atmospheric chemistry. So when I was doing like ozone pollution research and also like volatile organic carbon, and then the government encountered a problem like the digestate from the anaerobic digestion of the pig manure and also agricultural waste. They are commonly used as an alternative of the fertilizer in agricultural application. But as we all know that the heavy metal in the digestate could contaminate our land. So we are trying to find a way to do like the valorization of the solid digestate. So the ideas comes out from. So as I mentioned, the anaerobic digestion not only produce biogas, but also byproduct biogas residue include liquid and solid digestate. A nutrient-rich byproduct containing organic digestate matter and also metals. So the problem is, as I mentioned, the heavy metal content in solid digestate. So we are trying to use it as a feedstock of the biochar, and then being an absorbent to absorb the toluene, which is also a kind of main precursor of the ozone formation and also secondary organic aerosol in the atmosphere. And then we trying to validate the usage of the VOC saturated biochar as a solid recovered fuel, which is regarded as a green energy. So this is the schematic of this study. So as you can see here, we collect two kinds of the digestate. One is called pig manure. We denote it as the ADG. And another one is called digestate of pig manure and also agricultural waste. And then we use these two digestate to be paralyzed and then to doing modify with the potassium carbonate and called ABC, which is biochar, and also KABC and KCBC. And then we trying to use this biochar in the industry to absorb toluene, because the toluene in the atmosphere, in Taiwan, kind of like is higher than the other country. We don't know why, maybe it's the resource of the industrial emission. And then finally, we're doing the calorific value test and the determination, and then trying to know if it could be one source of the energy resource. And then this is the, I just briefly show the system of how we did. And then this is the system for the production of the biochar. And so before the pyrolysis, we are trying to improve the porosity of the biochar. So before we pyrolyze the samples, we are trying to use the potassium carbonate to modify the biochar. And then the temperature was wrong, the thermal condition was running at the 500 to 800 Celsius degree. So this is the absorption system, consists of three parts. One is toluene generation system, and another is absorption bed detection system. So by observing the breakthrough curve, we can understand the absorption capacity of different samples. So these are all the experiments we did. We did the automated analysis to understand the property of the samples, and also approximate analysis to understand the moisture, age, volatile matter, and fixed carbon content of the sample. And in TGA, we can understand the sample weight variation with the temperature, which could be understand the stability of the samples. And BET, we understand the specific surface area, which is very important to the absorption capacity of the biochar we made. And then the calorimeter, we can understand the heating value, like lower heating value, high heating value of the biochar, or we say the energy source. And then the HTDSC, we can understand the energy demand. We also monitor the electricity we cost during the production of the biochar. Because we will do the LCA. Actually, we just finished the life cycle assessment for the whole experiment, and to compare to conventional method. But I didn't show the result of the LCA. So let's move on the result discussion. So yeah, just very common result like elemental composition. As you can see here, the hydrogen and oxygen content decrease with the temperature. But as you can see here, the ABC 700, 800, it increased because we think the pore structure in the biochar may be collapsed during the when the temperature exceeds 700 degrees. We can observe that KCBC and KAPC still has a higher carbon content in the biochar. As for the Van Quevelen diagram, as you can see here, the y-axis is the ratio of hydrogen to carbon. So when it's getting a lower hydrocarbon to hydrogen to carbon ratio means the sample is more aromatic, which could be more stable. And for the x-axis is the oxygen to carbon. When a lower oxygen to carbon ratio means less oxygen containing functional group in the biochar, and then it could be more hydrophobicity and also be stable. So as you can see here, when the temperature increase, the sample or the biochar produce getting more stable. So proximate analysis of the biochar sample shows the volatile matter decrease with the temperature increase, and the fixed carbon again increase with temperature, but from the temperature 700 to 800, it's like showing a big decrease. Again, it's all about the structure of the biochar and the collapse, and then the structure change. As for the age, as you can see here, the modified biochar shows the less H content, which is more appropriate for the SRF, like solid recovered fuel usage. So for the left-hand side, the figure shows the TGA like mass reduction. So the ADG shows a higher mass yield compared to the CDG. We attribute this to the higher lignin content in the ADG. As for the right-hand side, as you can see here, there's a big mass reduction in CDG at about the temperature 300. For the 100 is more about the moisture loss, and then 300 is about the higher hemicellulose and the cellulose in the CDG. So you can those here, and then after that it's getting stable. So which means the material is quite suitable for the usage of as a absorbent. So for the surface area, I think as you can see here, the modified biochar has the highest specific surface area, which is good for the like air pollution control by absorption. And CDC as well, as you can see here, it reached to 1,000, more than 1,000. So this is SEM image of the raw biochar. As you can see here, it's a rough surface and also rough texture here. And then SEM of modified biochar, you can see that it's more spongy and also more small pores in the material. And there's also for the left-hand side, upper left, it shows ABC and CBC, and the absorption capacity for ABC is higher than the CBC. But as you can see at the bottom, the modified biochar samples shows very high absorption capacity, about like 10 to 20-fold enhancement compared to the those without modification. So the right-hand side is the comparison between the material we met in this study compared to the previous to other method. So as we see here, the absorption capacity in our material is comparable to the others and even better for the KCDC 800. So for this one is the kinetic parameter. So basically we did this model for this kind of experiment. So for the pseudo first order, it shows the biochar met at the lower temperature. It shows more active side. But for the in terms of the pseudo second order, more complex interaction can be seen, which means that chemisorption could happen, or other electron transformation could happen when it absorbs the toluene. As for the interparticle diffusion model, it shows the highest correlation, and this means the biochar doesn't hinder the diffusion from surface to the interior of the toluene. So I mean, the diffusion also acts as an important role during absorption. So the isotherm model, it shows that KABC and CBC has a higher absorption property. As for the low heating value, which is an indicator for if you can use as an SRF, so based on the ISO 21640, SRF can be categorized into 5 grades. So as you can see here, the 5th grade, in our material, KABC 700 and KCBC 800 even can achieve and higher than the 5th grade, which means the material we use and the whole method can be a potential way to valorize the digestate. For the energy demand, basically for the red one is about like 37 megajoule per kilogram we spend. But based on previous research, it's about like 80 megajoule per kilogram for the commercial granular activated carbon. So which means it could be effective way to reuse this digestate. So for the comparison of the energy performance in this study to the other study, as you can see here, the energy density, especially for KCBC 800, is higher than the others, which is also correspond to the high heating value for the first column. As you can see here, 37.9. So it's a very promising result. So the conclusion of this study demonstrates the potential of converting biogas residue into biochar and achieving dual benefit in waste management and energy production, and also, as I said, air pollution control. And the optimal biochar is with the following key features. I won't go into detail. The KCBC 800 shows the highest performance in our study. So this conversion process applied with circular economy principle and also can be a method for the net zero, even negative carbon emission. So also we can integrate the waste management and air pollution control, fostering the agro-industrial symbiosis essential for stable development. Yeah, that's it. It's all about my today's presentation. Thank you.
It's very interesting talk. So I think we can open the floor for few questions. Any question from the floor? Okay, maybe I can ask one question. So, you know, in Hong Kong, we actually burn the sludge and we generate electricity because we can't afford the land for the landfill.
Yeah.
So what is your current practice of dealing with this the biosolid? And do you think your research can, so do you plan to kind of scale up to have a real application, or this is just lab scale?
Yeah, currently in Taiwan, of course they use in agricultural application, of course, or they just deliver it to the fire plant and burn it as a fuel. But as I said, the moisture in the digestate is still high, so maybe it would affect the combustion efficiency. So with this way, I think I do this as again, it's like our government encounter, like they don't want them to use in agricultural application if it contains the heavy metal in the digestate. So yeah, I'll try to find different way to deal with this issue. Yeah.
So once again, thank you very much, and let's give him a big hand.
Next speaker is my colleague, Prof.